Let me make it nice and solid. That's the solid we would get if we were to wrap that region around the y-axis. As a comparison, this is it wrapped around the x-axis. And you can see these are completely different objects, right? Completely different, so they should have completely different volumes, all right? But we cannot use washers, right? Because that shape, when I wrapped it around the y-axis, was not a washer, was it? What was that shape? We haven't even talked about that shape yet, have we? So we're going to need to talk about that shape first. And back all this up. Go back. Let's go back right there and look at that shape. When I wrap that around, what we call this is a shell, all right? We call this a shell. And so let's see if we can't draw that shell on the page over here. I'm gonna have to redo all that. But let's draw that shell and see if we can come up with what its volume is. Because remember when we wrapped the rectangle around the x-axis, we got a washer, and we had a formula for what a washer's volume is, and then we used the integral to add them up. What we need to do here is see if we can find a volume for this, all right? So let me bring that over here. So we have this thing called a shell, shell, and it looks like this. Kind of like that, right? I would like to know what the volume of this is. Well, let's go back to the geometry here. Is there anything that we can tell from this picture? Let me bring my opacity out here. Make that less. You can still see it, right? There. Okay. Can you tell me how tall this piece is in relation to this picture here? It should be the blue one minus the red one, right? Whatever this blue function is, right? Whatever it is, minus the red one should be that height, right? Why don't we say, to make this easier, draw this over here. To go off of that picture, if we have that rectangle that we're wrapping, right? Wrapping around, then if we call this, let's call the blue one the top function, okay? Let's call it the top function, yeah? Okay, let's call the red one the bottom, all right? Okay, top and the bottom. So this should be just whatever that top function is minus the bottom one. Y'all agree with that? Okay, so we at least have how tall this shell is. That we know how it connects to the function. As I move this thing back and forth, that's going to change, right? And it will depend on those two functions. All right, but how do we get the volume? Because we want the volume, right? So what we do is we imagine coming in here and taking a pair of like scissors or shears and just cutting this thing, right? Let's cut this thing and let's get it and let's lay it out flat. So if I cut that and lay it out flat, it'll look like this, right? But it'll have some thickness to it, like that. That's what that would look like if I cut it and laid it out flat. This distance from here to here is still the top minus the bottom, right? Can you tell me how thick it is? Well, in this particular picture, the thickness would be the thickness of the rectangle, right? And since these appear to be functions of x, right, the thickness of the rectangle has always been for us what? Dx, right? Dx. So that thickness should be dx. So this thickness here should be dx. See, do y'all see that this is a box, like a three-dimensional box? So the volume of this should be length times width times height, shouldn't it? Length times width times height. So I know how thick it is. I know how tall it is. All I need to know is how long it is, right? And this is the most challenging part, is to figure out how long this side is. And the way I'm going to do it is just to think about that geometry again. If we start out with a, if we start out with this shape here, right? This is a little bit tall, but we cut it, right, and we lay it out flat, then the distance from here to here is the same as the circumference of that circle, isn't it? It's the same as circumference. And circumference, the formula is 2 pi r. Right? 2 pi r is circumference of a circle. So 2 pi r would be this. 2 pi r, but what the hell's r? What's r? Well, r is the distance from the axis of rotation. Look, the radius of this thing is the distance from the axis of rotation to where? To the rectangle, right? To the rectangle. It's from the axis of rotation, which in this case is the y-axis, right? So from here to the rectangle. So what I do here, what does it say on your formulas? I think it says r sub x. Make sure I follow the, yeah. No, I just call it capital R. Yeah, I just call it capital R. So I call this capital R on the formula sheet. And what this is, it says it on your formula sheet, is what? That is the distance from the axis of rotation to the rectangle. Not to the outer edge or inner edge, not R out, R in. It's the distance from the axis of rotation to the rectangle. So for us in this problem that I just had up here, what was that distance? Let's go back and look at this problem, or this illustration here. If I swing this back up like this, what is the distance from our axis of rotation, which is the y-axis, to that rectangle? X, right? Didn't I start class and I said there's something I want to point out that I didn't point out before, that when you do an integral, right, the distance from the y-axis to the rectangle is always x. So in this particular example, that would be x, all right? So let's stick with this example. I'm going to replace this with x for this example. You all okay? All right, so can you tell me the volume of this then? What is the volume of this? It should be 2 pi x times top minus bottom. I'll put that in parentheses. I'm going to put t minus b instead of top minus bottom. Top minus bottom, and then dx. That is the volume of one of these, right? Of one of them. One shell. That's the volume. How do I add them up? Use the integral, right? I use the integral to add them up. So I bring in the integral. Okay, limits of integration. Well, what's the thing that's changing? This rectangle, right, is moving from the left edge to the right edge. What's changing, x or y? X, right? The x. So your limits of integration are going to be this left endpoint, this right endpoint. So your integral should go from a to b. And then it's going to be this formula, right? 2 pi x times top minus bottom dx. And what can you always pull out of that integral? 2 pi, right? Now be careful. This x is only x in this particular problem that you're looking at right here. If I change the axis of rotation, move it somewhere else, then you're going to be having to figure out what it is. All right? Top minus bottom, that's just the top function minus the bottom one, right? So let's go back to our formulas that I printed out for you. And let's look at that master formula we have here. This is it right here. So this is it with specific things put in place, right? Say, hey, you see this region? We want to wrap it around a vertical line. Notice that the rectangle is parallel to the axis of rotation. Can't use washers, must use shells. Okay, so what we do is we need, well, you don't really need all this. This is where everything kind of comes from. But to set up the integral, this is what you need. 2 pi, got it, right? A to b, that's your limits here. right? Start and stop. R, that's the most complicated part of the whole problem. It's figuring out the distance from the axis of rotation, to your rectangle. This right here is the y-axis. From the y-axis to the rectangle will always be x. So we'll need to know what this distance is to figure out r. When we do an example, you'll see it. Then this is top minus bottom, right? Top minus bottom, and then dx. And that's it. Yes or no? I mean, I need to do an example, but do you see the geometry of it? Okay. I hope also what you're seeing is, again, the integral is a tool. It helps us add things up. What we're adding up depends on what we come up with geometrically. Yes?
I know you mentioned we can't have that on the test, but like...
you can have it.
I can have it on the
in your head.
Oh, okay.
Yes, you can.
So we
Absolutely.
Can't write it down anywhere either, right?
So if you're not a memorizer, do what I did, and that's know it for about a minute, and when the test is handed out, you write it down.
Oh, okay.
Yeah, because I wasn't a big memorizer either, but I don't want to. I mean, you do have to remember some things, and yeah, I mean, yeah, just look at it, and when I say it's time to start, put it away and just write it down. Hopefully, for that minute or two, you'll remember it.
Okay.
Or you can get the tattoo. Permanent tattoo.
Someone,
Permanent tattoo.
someone genuinely put formulas on themselves.
Sure, sure, absolutely.
Honestly, that would be dope.
Yeah, I mean, I don't recommend it. They wouldn't look good later in life. You know, the formulas.
It depends on how big you get. If you get really small, it's yucky. But they get like huge.
I wanted to get a tattoo of this thing called the Schwartz inequality. It's really, the way my professor described it is it's the inequality that prevents the universe from collapsing upon itself. Anyway, I was going to get that done, but it's got way too much detail in it, and so like it would have been, yeah, it would have been huge, but then even then it would have, you know, faded out and blurred. All right, I'm ready to do that example. You ready to do that example? All right, so we have, what was it, y equals square root of x, we have y equals 1 over x, we have x equals 3. And we want to do this about the y-axis. We want to do it about x equals, what did I say, -2 and x equals 5? I think that's what I'd put. Okay. We're going to draw some pictures. I'll take my time on the first one. We already had Desmos do this earlier, but there's square root of x. Here's 1 over x. X equals 3. That's not an axis of rotation, right? X equals 3 was given to us as a boundary to help close the region out, right? So our region is this thing right in here. Now, would you agree vertical rectangles are perfect for this region because you have functions of x, right? So I want to use vertical rectangles. I want to do that, right? So if I put a vertical rectangle in here like this, I have a top and a bottom, right? It's pretty clear. I have a top and bottom. My axis of rotation for part A, my axis of rotation is the y. God, this one does not want to cooperate. My axis of rotation is right here. I know where they hit each other, right? This we had solved earlier, beginning of class. That was 1. We got that by inspection. And then 3 was given. So I'm going to use shells because my rectangle is parallel to the axis of rotation. That's shells right away. That's the thing that lets you know. Shells. So since I'm using shells, I know that my formula is going to be 2 pi integral, okay, starting where? 1 stopping at 3. Okay, now, capital R. The distance from the axis of rotation, which is here, to the rectangle, right? The distance from here to here is r. Now, it just so happens that because the axis of rotation is the y-axis, r is also x, right? Because we said, beginning of class, the distance from the y-axis to the rectangle is always x, right? I told you that in the beginning. x is going to go from 1 to 3. So x is going to start at 1, end at 3. So the distance from the y-axis to the rectangle is x. So what will r be for us? X. And then, parenthesis, top function, square root of x. Not squared, just square root of x, that's it. Minus bottom function, 1 over x, close, dx, done. That's it. And of course, you could distribute that through, and then you could use, power rule to find the antiderivative. Yes?
The R, where's the R?
R is always the distance from the axis of rotation to the rectangle. So for us, R is from, this is the axis of rotation, this is the rectangle, that distance. You have to, the reason we know that it's x is because I said in the beginning of class that whenever you draw this rectangle, the distance from the rectangle to the y-axis will always be x. And since the y-axis is our axis of rotation, that means R is x. Okay? Everyone good? We're done. We're done with that one, part A. Part B, x is negative 2. I'm going to draw it again. Sorry, I will. It's important that you see the difference between these pictures. It's not a big difference, but it is different. So here, square root of x. Okay. X is 3. Got my rectangle in here. My axis of rotation now, x is negative 2, is over here, right? Negative 2. Axis of rotation. Vertical rectangle, vertical line, parallel, shells, right? Do I have a top and a bottom? Yes. Do I know my limits of integration? Yes. All I really need to know is r. So r is the distance from the axis of rotation all the way to my rectangle, right? What I know, though, is that from the y-axis to the rectangle is what? X. And from here to here is 2. And we look at it like a distance, right? So r is x plus 2. That's what capital R is. It's x plus 2. So my integral will look like this. I'm going to leave that one up there. It's going to be 2 pi integral 1 to 3 x plus 2 must be in parentheses, then square root of x minus 1 over x dx. Top minus bottom, dx, that doesn't change. The only thing that changes is this, x plus 2 versus x, right? Any questions?
Why would 1 to 3 not change?
Because remember, the 1 to 3 is just telling you where you're going to let your rectangle move through, right? Your rectangle is going to start where they hit each other, right? You're going to have really infinitesimally small rectangles, and then as you move to the right, they're just going to move across, right? Where's it going to start? At 1. Where does it stop? At 3. That doesn't change. The fact that your axis of rotation is further away, these shells are going to be bigger, right? Like imagine go back to this problem right here, the first one. This is our axis of rotation. If I wrap this little rectangle around the y-axis, I'm going to have this small shell right here, right? But if I do this small rectangle around that axis, it's going to be a big shell, isn't it? The part that accounts for that is this, right? This is the height of the shell. This is how far away. This is your radius. So 2 pi r, right? All right, so last one, we're going to go around x equals 5. Last picture. All right, so if we do this one, square root x, I'm just gonna write square root x. This one, 1 over x. X is 3. Axis of rotation. direction is 5 over here. All right, vertical rectangle, perfect, right? They're parallel shells. Top and bottom, got it. Limits of integration, got it, right? The only thing I need to know is R. The distance from the axis of rotation, to your rectangle. That's this distance right here, from here to there, that's R, right? That's what I need to know. What is that distance? And the only thing I do know is that from the y-axis to the rectangle is what? X. Right? So what's R? 5 minus X. Because you know that the distance from the y-axis all the way over, right? From here to here, that's 5. So you don't want all of 5. You want a 5 and you want to take away this X. And that will give you what remains. So it's going to be the same. Can I just adapt this formula right here? Just put this in. All I'm going to do is 5 minus X. That's terrible. 5 minus X. There we go. That's the answer to part C. Slight change. I think shells is actually a lot easier to do the different variations of it because it's just what changes with R. All right. Let's go back to the problem that I gave you. Where was it? How are we doing on time? We're doing good. Okay. I need to find this. So I asked you to do this problem, right? Those 3. So you can see on the review for this exam, I asked you to do those 3 and turn them in for a quiz. These next 3, do y'all see that that's basically what we just did here, right? So on a test, what I've done in the past is I've given you a region, and then I ask you to wrap it around 3 different horizontal lines, which means you'll use washers. And then that same region, wrap it around 3 vertical lines, and then you'll use your shells, right? Okay. Now, let me ask you something. I don't want to go too far off on this little tangent here, but what if I gave you this? What if I gave you this region, I'm going to make it a nice, easy region to work with. What if I gave you the region y equals x, x equals 0, y equals 1? Let's draw that region first, and then we'll talk about it. So do we know what y equals x looks like? Okay, it's a diagonal line, right? This is y equals x. And then x equals 0. X is 0 is the y-axis, isn't it? Y equals 1. Horizontal line. All right, y'all see the region bounded by all those? That's supposed to be on the y-axis, sorry. There. There, okay. So the region bounded by all of those is this region right in here. Now, if I asked you to wrap this around a horizontal line, either the x-axis or below it or above it. Oh, by the way, I'll never ask you to wrap something around a line that goes through it, because then it's weird, like what happens then, right? You get like a double volume. We don't do it, all right? So what do you think? If I give you a horizontal line, what method are you going to use? Washers or shells? I mean, it's kind of up to you. If you're going to use washers, right? Let me give you some arbitrary horizontal line. If I give you that line, I want you to wrap it around that. Then you're going to use washers. If you're going to use washers, then what does your rectangle have to be? It has to be vertical, right? Which means that these have to be functions of x, right? They have to be. Are they functions of x? Are they both solved for y? Yes, right? So you could do that with shells. Let's put a number. No, I'm not going to do it. So this right here, drawn this way, you'd use washers, right? Yes? Now, what if I ask you to wrap it around a line that's vertical? Use shells, right? Yes? But could you have done it this way? Could you have turned your rectangle over like this and wrapped it this way and used washers? Yes, but then you would have to solve this for x, right? There would have to be functions of x instead. That's okay. In other words, you have a little bit of freedom on how you do these. My recommendation is that if these are functions of x, then if you got horizontal lines, use washers. And if you got vertical lines, use shells. And then I think it's clean. If you try and go against that, like if you say, all right, I want to do this region around this line, but I want to use washers, then you're going to have to change these over to functions of y instead of x. So it's just more work for you, all right? By the way, could you do this? Could you go this way and around this? Yes, but it would be a shell. And I haven't shown you how to do one of those, right? And I'm not going to, because I think we have enough tools in the toolbox to survive. I think we can move on. But in real life, like in the big picture of things, you should be able to do washers in both directions and shells in both directions, just depending on the problem you're given. I normally stick with functions of x on the test. Yes?
So, just to reiterate, make sure we're stuck with it. So if the axis rotation, gracious, what's it hard? It's horizontal, then it's better to do a washer. And then if it's vertical,
If your axis of rotation, so I think you should start that with, if you have functions of x to start with, right? That means you're going to use vertical rectangles, right? And so if you have a horizontal axis of rotation, you're going to want to use washer. And if you have vertical axis of rotation, then you're going to want to use shells. Yeah. I would always say what dictates it is what your rectangle needs to be. Your rectangle in the region, if that's a vertical rectangle, that dictates everything. If it has to be horizontal, the bonus question with the sign going up the y-axis, there you have really no choice but to use horizontal rectangles. No choice, right? All right, but that problem on that bonus was not a rotation, was it? It was just an area problem, so we weren't wrapping it around any axes. All right, we are done with solids of revolution. But we're not done with 7.2. As many years as I've been teaching this class, I can't figure out how to do this next section, this next part of this section, in a way that people are like, yes, I understand that. Makes perfect sense. But, you know, I always get to try. Every semester I get to try something different. Here we go. I want you to throw out the whole thing about rotation and taking this region, wrapping around axes. We're done, okay? We're starting from scratch with a new picture, new idea, but we're still in 7.2. So what you see here is a region bounded by two curves, right? There's a region bounded by two curves. Let's look at it like straight on. There we go. It's a parabola that opens up, parabola that opens down. Let me draw that over here. Parabola that opens up, parabola that opens down. They hit each other, happen to hit each other on the x-axis. Who cares? All right. So I'm going to describe to you verbally this solid object, all right? There's some solid object right here. You can't see it right now, but I'm going to start describing it to you, and hopefully you can start to see it, all right? Here's what it looks like. This is what I'm going to tell you it looks like. This solid object, the footprint of this object, like if I were to set it on the ground here, the footprint of it on the ground is that region, right? So I guess if you were shine, no, I don't want to say that. Let's say we were to put like something, paint on the bottom of it, right? And just like a stamp, just put it on the ground, then pick it up. That we would see this whole region here on the ground. Got it? So the way I'm going to say that is the base of a solid is the region bounded by these two curves. Make sense? The base of a solid is that. Now, this solid, let me put it down on the ground. I'm going to come through here. Where's my sword? Oh, there it is. Okay. So what I'm going to do is I'm going to put this on the ground like this. And I'm going to come through and I'm going to kind of orient when I place it on the ground. So it's like the XY plane is the ground now, right? I place this solid down on the ground. I've oriented perfectly just like this on the ground. And what I'm going to do is I'm going to come through here with a sword and I'm going to cut through this solid. So the solid's coming out at you, but you don't know what it looks like yet, right? Other than that's the footprint. So what I'm going to do is I'm going to cut through it, but I'm going to turn my sword so that my sword is perpendicular to the x-axis, right? So my sword's not this way or that way. My sword is perpendicular to the x-axis. And when I cut through it, right, it's like a piece of cake, right? I'm going to cut through this, and I have this piece over here, right? And when I take that piece and I turn it and I let you look at it from the side where I cut it, I'm going to tell you it's a square. Okay? So let me cut through here. Let me cut right through there. If I were to cut right through there, right there, and let's make it like a little piece of cake or something. This is I'm gonna slice right next to it like this, and take that little slice of it, right? And I'm going to kind of bring that slice out, and I'm going to turn it to the side, and I'm telling you, when you look at it, it looks like a square, perfect square. Now it has a little thickness to it. See that? So that's the piece I've taken out. I'm telling you it's a square, all right? Still good? Okay, what would the slice down here look like if I did the same